Okay, so let's move on to section 5.2. We will introduce the electrical vector potential, which is usually known as the voltage, electric voltage. And we will look into the relationship between electrical field intensity and voltage under the condition of static field. Then we will try to solve some problem using the superposition law. That is, given the electrical potential distribution from a simple point source, we can use the superposition law to derive electrical potential of a geometrically complicated structure with a more complicated charge distribution. And so we will look into example 5.2, which is a case of electrical dipole, and example 5.4, which is infinitely long electrical charge lines, and we're looking into the magnetic vector potential. So originally in section 5.1, we have this relationship. The electrical field intensity can be generated by the gradient of phi and the time derivative of A under the condition of static field. 进场的时候, under the condition of static field, the second term goes away, the time derivative of A goes away, so it can be expressed E equals to the minus of the gradient of phi. Phi is the electrical scalar potential. And here's an important relationship between phi and E. Because phi and E are related with this relationship. Not that this relationship is only true under steady field condition. Otherwise, if this is time variant field, you will have another term over here. So this term will perturb, 混乱, 搞乱, will perturb this relationship. Okay, so what relationship? That is the direction of E and the direction of gradient of phi must be perpendicular. They are orthogonal to each other. Okay, E is a vector, so it has is a direction line, can be expressed with this black arrowhead. Okay, the electrical field intensity, it has magnitude and direction. Phi, the electrical scalar potential itself, is a scalar. It is a scalar. However, if you taking the gradient of phi, it end up with a vector. Okay, well, what a vector? The opposite of E. Okay, so before you taking the gradient of phi, you have these surfaces, these planes. These surfaces are formed with points of the same phi. So this surface is referred as the equal potential surface. 等电位面，等电位面或者等电压面或等电压线这样子啊，在3度空间里头是等电位面啊。So the figure shows equal potential surfaces of different phi values. If you taking the gradient of phi, you are pointing toward the direction of higher potential or smaller potential. Okay, if you taking the gradient itself, you should pointing toward the direction of higher potential. On the other, however, the electrical field intensity is defined as from greater potential to smaller potential. So you need the negative sign over here to find the direction that is consistent with the definition of electrical field intensity. All right, so the thing we need to remember here is under the condition of static field, the potential, equal potential surface is always perpendicular to the electrical field intensity direction 啊，在进场的条件下，电场跟等电位面一定是垂直的，或等电位线一定是垂直的。Alright, so for two equal potential surface, that is phi A and phi B, the potential difference is simply the subtraction of the two, right? Phi A minus phi B. And it can be also expressed with the line integral from point B to point A. So it can be expressed as the line integral from point A to point B that it sums up with the potential difference. And the potential difference d phi can be expressed as the dot product of gradient of phi and dl, the path. Gradient of phi is the rate of change. The dl is the path direction and the path distance. So if you change the order of A and B, you only need to add up a negative sign over there. So here, according to the definition of this, that is, the gradient of I under the condition of steady field, the gradient of phi is the minus of E. Okay, so you can substitute gradient of phi with E over here. Be careful about the sign. Okay, it changes if you integrate from A to B or B to A. So the potential difference is the line integral from that line integral of electrical field intensity from A to B or B to A. So the potential difference in the static field case has the same meaning as the voltage, and they need to be consistent with the so-called conservative field, 保守场. Do you know the example of conservative field? Can you give me some examples? Yeah, gravity field is, of course, and you get example of the conservative field and well, steady electrical field or steady magnetic field are all conservative fields. And so what happens if you have a conservative fields? If you have conservative fields, the closed loop integral should be equal to 0 at all times, which means the magnitude, the quantity of this physical parameter is only a dependent of position, not a path. Okay, not a path. Your gravity potential at the floor at the fifth floor is higher than your gravity potential at the fourth floor. All right. No matter which fourth floor, fifth floor, or fourth floor you are, well, it's only determined by the distance between the gravity center of Earth and your position. All right. So here is the Faraday's law. Okay. So Faraday's law comprise description about time variant field. How do you know that? Well, you have time derivative over here. Okay. So what happens if this is under the condition of steady field? Then curl of E must equal to 0, right? So if curl of E equal to 0, then the Maxwell equation in integral form should be equal to 0 as well. So the closed loop integral of E should be equal to 0 as well under the condition of steady field. On the other hand, if you don't have if the steady field condition is not true, then the closed loop integral will be depend on time, depending on how much change of magnetic flux passing through the surface enclosed by the loop C. Okay. So under the condition of time variant field, the potential difference is a function of path. Now, if you have a bigger loop, you may end up with small potential difference. If you have only small loop, you have smaller potential difference. If the rate of change of B is larger, then you end up with higher potential difference. On the other hand, for steady field, then the closed loop integral of electrical field intensity should be 0 at all time. All right, so that's it. So under this condition, we can, under the static field condition, we can substitute phi with V, that is the voltage that you are used to. So electrical field intensity is the negative of gradient of V. Okay, so here we define we define the electrical scalar potential as V, the voltage. So let's review some fundamental problems. In chapter 1, we use the Coulomb's law. We find out the electrical field intensity due to a point charge according to the Coulomb's law, which is observation made with experiments. Okay, so back then we defined the expression of point source electrical field distribution directly. And here, because we introduced the definition of electrical scalar potential, there are some alternative, there are some alternative to define the to find the electrical field intensity due to point charge distributions. So let's see. So what is the electrical field intensity built up by point charge according to the Coulomb's law? The electrical field intensity is written as 4 pi epsilon r squared times Q. Okay, so it's proportional to the amount of charge and reversely proportional to the distance to the observation point, and the direction of electrical field is symmetrical as a sphere, like this. And if the charge polarity is positive, 正极了，正电荷. If the charge polarity is positive, then the electrical field is pointing outward. On the other hand, if you have negative charge, then the electrical field is pointing inward. Remember that we already say the equipotential surface is always perpendicular to the direction of the electrical field. So we know the electrical field built up with a point charge is like arrowheads pointing outward in a spherically symmetric fashion. So the equal potential surfaces due to the point, because of the point charge, should be concentric spheres. 同心球了 concentric 啊，同样的 concentric spheres like this. Okay, and also the electrical field intensity can be expressed as the negative of the gradient of phi. So actually, we can find out the electrical scalar potential phi using the integration of E, right? So let's try to do this. So because we define E equals to the negative of gradient of V, then dV, the potential difference. Suppose we have okay, first and first. So here we are trying to do the integration in which coordinate system? Spherical coordinate system. Remember that I said the spatial derivative in spherical coordinate system is somewhat tricky. It may involve theta and phi other, because the all three axes in spherical coordinate system are not independent. Fortunately for this case, because the field built up by a point charge is spherically symmetric, so we only have to deal with direction r. So we don't have to worry about theta and phi. So the derivation presented here are more straightforward, more simple. Okay, but be careful if you have if you involve field projection on other axes, the derivation can be more complicated. On the other hand, this case is relatively simple. You only deal up with r direction. All right. So what is dV? The potential difference between two spheres. Suppose because in the previous slide we saw that the so-called equal potential spheres are spheres enclosing the same origin. So dV is the difference between this sphere and this sphere. So you kind of, how do you find the voltage difference dV over here? You do the you take the product of distance dl and the gradient of the gradient of the gradient of v. Okay. And we already know that the gradient of v equals to e, or minus of e. So so you see we use the expression of electrical field intensity directly. So we put it over here because we know this equals to the minus of gradient of v. Okay, so we put it over here. And the distance between two spheres is suppose is r, so it's dr over here. And this thing can be identified as the derivative of this. Okay? So this is r to the square. This is r. So if you perform the derivative of this, you get r to the minus 2 with a minus sign in the front. And the constant goes away. 所以我们等于是 把它给积分积上去了哈，去猜它原先积分原先在微分之前的样子嘛，所以你从 r 的负2次方的关系变成是 r 的负1次方啊。So we kind of identify the formulation of v like this. So after the integration with respect to r, we found out the electrical scalar potential of a point charge. We perform the integration of the electrical field intensity distribution of a point charge to find out its electrical potential. From the field, we take the integration of the field to find out the potential. And as you can see, it's spherically symmetric as well, and it's inversely proportional with r, with respect to r. And it's also proportional to the charge, the amount of charge Q. And well, how about C? Can we determine the value C? Well, the answer is you can, for this case, you can set C equal to 0, which means we set up the voltage reference in the position at infinity. 我们把无限远的地方的电压设为0。好，我们把无限远的电压设为0。好，把电位的参考点设在无限远处。所以自然它的那个电压的影响到我们现在的观察点附近的时候就看不到了，等于0。那这样是比较方便的哈。不过只有在球坐标系统里头是如此哈。我们今天会，假如有看到下一个 example 的话，你会发现不是这件事情哈。So for this problem geometry, it's convenient to set the voltage reference equals to 0 at the infinity. At an infinity distance, okay, so the voltage formula can be, the voltage expression can be simplified as equation 5.35. So V is inversely proportional to R and is proportional to Q. Do you remember why we have 4 pi over here? Why we have epsilon over here? Epsilon is the description of the environment, okay, the permittivity of the space. So if this is a vacuum space, if this is the free space, then epsilon equal to epsilon 0, which is equals to 8.854 times 10 to the minus 12. And what is the significance of 4 pi? Well, because the distribution of electrical field, the distribution of electrical potential are spherically symmetric. And the radiant, the surface of a sphere is 4 pi, right? So the next thing is, once we find out the voltage, once we find out the voltage expression for a point source, we can use the superposition law to find out the voltage distribution of a complicated source. Okay, that should be in the next slide. Okay, this slide just summarizes what we have, what we observed from the previous result. So the first case is example 5.2. Suppose we have 2 charge in the space. One is a positive charge of plus Q. The other is a negative charge of minus Q, and they are located near the center of the coordinate system with equal distance. That is, from the origin to positive Q is half d. The distance from the origin to minus Q is half d as well. So the two, Q and minus Q, the 2-point charge, form the so-called electric dipole 电偶极啊，电偶极由相同电量、不同电性的电荷所组成。And so electrical dipole is important in not only in electromagnetics, it's important in physics and chemistry as well. Why? Because the atomic structure or molecule structure can be, when it comes to charge, it can be most of the atomic structure and molecule structure can be separated into a group of positive charge and a group of negative charge. Then those charged particles, the behavior of charged particles are affected by electromagnetic fields in the background. Okay, so and in section 4.2, which I skipped in the last semester, I should there is physical quantity called electrical dipole. It equals to Q times D. This is so-called electrical dipole moment. 我不知道马老师有没有教，杨老师有没有教？我是没有仔细讲的，好像快带过吧。好，这叫做电偶极矩 （electrical dipole moment）。Is the product of charge and distance. So if you have a positive charge and negative charge, Q and minus Q, and this distance of D, then you can define the so-called electric dipole moment according to the distance and the amount of charge of the electrical dipole. So as you can see, the greater the charge Q is, the larger the distance D is, you have greater electrical dipole moment. So in general, molecules which is separated further and with small charges in the positive part and the negative part, usually end up with a larger electric dipole moment. Electric dipole moment than atomic structure. 所以大分子的那个电偶极矩会比小的分子的电偶极矩来得大，所以这当然会影响到它们的一些化学特性。那这边我们来检视一下电偶极矩 （electrical dipole moment） 它们所造成的电场的影响。But let me ask you a question first. You should answer it. You should answer it according to your intuition. 直觉上来回答。What do you think of the impact of electrical dipole or a standalone electric charge? Which has more impact, or which one should build up more or most significant electrical field? 你觉得电偶极矩所建立起来的电场分布会比较大、比较明显、比较重要，还是单独的电荷建立起来会比较大？那我们看 ，OK， 好，我们看看结果怎样All right. Of course, here we have two-point charge. One is positive, the other is negative in terms of polarity. 它们的极性。So one is Q, the other is minus Q. So what is the potential built up by the two charge? Suppose P is the so-called observation point. So as you can see here, we are looking at the problem in the spherical coordinate system. So the position, the location of P is specified as R, theta, phi. So you know this is in spherical coordinate system. And according to the potential expression of a point charge, that is Q over 4 pi epsilon r, the voltage at P can be expressed as 4 pi Q over 4 pi epsilon r sub 1 plus, well, which you end up with minus, because you have a negative charge here, minus 4 pi epsilon r sub 2 Q over 4 pi epsilon r sub 2. So you end up with this thing, okay? So in the front it's Q over 4 pi epsilon, but in the rear is 1 over R1 minus 1 over R2. How about the difference between R1 and R2? Well, they should be of similar values. In particular, when your observation point is placed away from the origin. Okay, if P is very close to the dipole, then R1 and R2 are of different value and different directions. But as you can see, if I move P away from the origin, then the direction of R1 and R2 becomes roughly the same, and the distance are about the same as well. However, they are about the same. They are not the same, right? They are not the same. So what can we do is to approximate, to find out an approximation of what we have in the small parentheses, so that the problem can be simplified. So if P is placed far, far away from the origin, then we know that the line R1 and the line R2 are about in parallel. And the distance is about the same. However, there are some difference. The difference can be expressed as the projection of d over 2 times cosine of theta, right? And, well, this is only half of the difference. The other half of the difference is d over 2 times cosine of theta, cosine of theta. So R1 can be approximate, not this approximate size. So they are not exactly the same, okay? The approximate only valid when R is a large number. 你说 R 怎么决定 R 是一个 large number? When R is much greater than D, okay? When R is much greater than D, then this approximation becomes valid. So R1, which is shorter according to the plot, can be expressed as R minus D over 2 times cosine theta. And R2 can be expressed as R plus D over 2 times cosine theta. Okay? Acceptable, right? So use the two approximation. This is the exact form. This is the exact form. So you have the equal mark. But you can apply the approximation of R1 and R2, and you end up with this expression. The difference between 1 over R1 and 1 over R2 is d cosine theta time divided by R to the square, divided by R to the square. So here is the sum of the two. The voltage potential, the voltage built up with an electrical dipole, can be expressed as QD cosine theta. So you can identify that the first two is the electrical dipole moment, okay? So it's proportional to the size of D, proportional to the amount of charge Q. So if you have a bigger or larger electrical dipole moment, the voltage built up by this electrical dipole is larger, of course. However, in the denominator, you have 4 pi epsilon r to the square. Remember, for a single charge, the denominator is 4 pi epsilon r, which means the implication of this is the influence, the power of this electrical dipole moment is weaker than a standalone point charge, because its influence decreases as R increases, and it decreases more rapidly than a single charge. Why? Well, it's not supposed to be difficult to understand, because you have a positive charge and a negative charge. One is pulling you away, the other is pulling you to the other direction, so their total effect is kind of canceled out, especially when you are observing at a very far distance. Okay? So, but anyway, you can, all right. So you, oh, another interesting thing is the cosine theta, which means what? So here is a positive Q, here is negative Q. So there, the voltage built up by this positive, negative is, so here is point A, here is point B. Which one is stronger? Use your intuition. A 比较强还是 B 比较强 ？A 嘛，为什么？因为这两个相同嘛，一去一回把它抵消掉了嘛，对不对？那这边的话呢，这个比较近啊，这个比较远嘛，所以 A 可能会比较强一点。所以你看那个 cosine theta， 假如我们刚才没有讲的是，它是沿着 z 轴摆啊，所以这个夹角是 theta 角。Okay, so theta angle is the angle between the observation point and the z-axis. So cosine, when theta equals to 0, cosine theta equals to 1. On the other hand, if your observation observed from the side, theta equals to 90 degrees, and cosine theta end up with 0. Okay, so electrical potential of an electrical dipole is 0 on the horizontal plane. Is 0 on the horizontal plane, and is stronger on the direction of the axis. So once you have the expression for electrical, once you have the expression for electrical potential, that is the voltage, you can get the electrical field intensity expression using the negative of the gradient of V. Okay, so you just perform the differentiation of V of this, and you end up with this. Okay, so the first thing to note is that the influence of the electrical dipole is still proportional to the electric dipole moment. However, its impact, its importance is decreased with r to the cube. R to the cube. So its influence dies out more quickly as you move away from the origin. And the field built up by the electrical dipole moment is what? It's not isotropic, it's not homogeneous in this spherical space. As you can see here, the electrical field intensity have R component and theta component. But because you place the electrical dipole along with the z-axis, it's still symmetric in the phi direction. So you have no phi dependence in this expression. 那当然，你把它横着摆的话，你就有 phi expression 了哈。不过干嘛给自己找麻烦呢？所以摆在 z 轴上，它是轴对称的哈。 So as you can see, the electrical field intensity is also a dependent of theta coordinate. Theta. It's stronger on the top and weaker on the side. And so below is the electrical field intensity, as you can see here. So you can use this expression to draw the bold arrow lines over here. To draw the thin solid lines here, which are the equal potential surface, you can put up the this expression in the MATLAB. Okay, I strongly recommend it to have some certain degree to master the MATLAB, which will be beneficiary if you are dealing with some signal processing. OK， 我还是强烈建议大家要学一下 MATLAB 哈。Alright, so in the text it says that the equal potential surfaces can be described with r squared secant theta. Well, that is the inverse of this. Okay, so you put the cosine theta over here, it's become r to the square secant theta. So if r to the square secant theta is a constant value, you end up with circles over here with different r value. All right. So it seems with the help of electrical potential V, it's easier to find out the electrical field built up by the electrical dipole. So this is the first example we have to derive E in terms of V. So once you have V, you use V of point source and assemble them to form the voltage of a complicated source, and you taken the gradient of V, of total V, to find the total E from a complicated charge distribution. And we also know that the electrical field lines starts from positive charge and end in the negative charge, and the electrical field intensity lines is always perpendicular to the equal potential surfaces. All right, now let's move on to example 5.4, which is an example of infinitely long line charges of uniform line charge density low sub L0. And this line is located along the z-axis. And we want to find the potential made by this charge everywhere. Okay, remember that we have encountered this kind of problem in chapter 1, section 1.6 something. And remember, in that case, we kind of divided the line charge into two pair of short charges, right? So one is over there, the other is over here, and using the Coulomb's law, we know the E fields is due to this charge is point this way. The E field of this charge is point this way. So the vertical components are canceled, while the horizontal components can be ate up. So we divide the long line with infinite pair of small charges, and we perform integration from 0 to infinity so that we can have the total electrical field intensity on this point. Okay? So that's what we done when we don't know the existence of electrical potential. But this time we will try to solve this problem using electric potential. So here is the expression for point charge. Point charge. The electrical potential built up by point charge is this, Q over 4 pi epsilon r. And Q can be replaced with rho sub L0 times dz, the distance of the short line charge. Here we assumed the zero voltage position is here, okay? Well, your question is why not place the voltage reference at the infinity? The answer is no, that will complicate the math problem. Because if you remember, you know, the electrical field intensity built up by a line charge is what? log r 分之一是不是？还是 log r？ 反正是一个 log 值啦，对不对？哦，我忘记了呢。不对，不是这个，诶，不对，我想错，哎，没有，这里没有 log。好像类似这个吧，你们翻课本的那个第1章，大家可以找得到，类似这样子，反正会是 r 分之一的关系。Alright, anyway, so to avoid mathematical problem, we are assuming that this is the voltage reference, that the voltage here is 0, and we can find out the voltage here, P, as the difference between the two. So the voltage difference between the 2 points can be expressed like this, using point charge from here, okay. And the distance AP and the distance AP sub 0 are r to the square plus z to the square, and up sub 0 to the square plus z to the square. So we just use the geometric parameters drawn in this plot to form equation 5.38. Then this slide tells you that it's not appropriate to place the reference point, voltage reference points at the infinity, because we end up some natural log expression, which we will have some problem with that. So to get the electrical voltage built up, electrical potential built up by this infinite line, we perform integration of the line charge from z equals to minus infinity to z equals to infinity. So we end up with equation 5.39 over there. You take out some common things to the outside, and here we still have to do the integration, which looks a little bit scary. But don't be scared. I provide you all the mathematical tools you need in this slide. Okay? So we begin with this expression, and you can identify 1 over square root of r to the square plus z to the square can be substituted using trigonometry as second alpha. Alpha is the angle defined over here. So the first term is second alpha, from alpha equals to 0 to infinity, or to 90 degree, okay? So now that we take, so here we integrate from minus infinity to infinity. Here because the top and the bottom are symmetric, so we we change the integration limit to 0 to infinity. And here is the 2 taken to the outside. So z equals to 0 equals to alpha, is equivalent to alpha equal to 0. And z equals to infinity is equivalent to 90 degrees. So we replace the integrand from z to alpha. So the integrand becomes second of alpha times the alpha. And using the formula, okay, using the, well, you should look up your, 所以公式课本千万不要丢掉啊。所以你在后来有人把公式课本丢掉了吗？还是卖给学弟了？OK， 好，千万不要做这种事哈，因为你后面的电机系的课都会用到公数哈。好，所以公数的那个积分表，查积分表的话，你会看到这个东西的积分是这个东西啊。好 ，The integral of a second function is the log of second function plus tangent function. Okay, and you can replace this with this. And if you put z equals to 0 and z equals into infinity, these things will be simplified like this. Minus rho divided by 2 pi epsilon sub 0 times log of r over r sub 0. So if r sub 0 is, that is, the position of 0 voltage reference is placed at infinity, then the whole thing will go to 0, which is not defined for log function. So that's the reason why you cannot place r sub 0 at the infinity. Okay, but anyway, you can choose the voltage reference at any location, as long as it is not the infinity. Then you end up with this, the voltage expression for an infinitely long electrical charge line. What happens if you take the gradient of this thing? If you take the gradient of this thing in which coordinate system? Cylindrical coordinate system, of course. Okay? But as you can see here, it's only a dependent of r, not a dependent of phi or z, right? So the differentiation should be easier. So you take the derivative of this thing, you end up with what? With this, right? This thing. Log r 微分之后变成 r 分之一嘛，当然你还有一个 r 0分之一啊，我要那个再说吧。好，所以是不是这样子了？所以把这个东西在助坐标系统里头取 gradient 的微分，就会是我们以前看到积分出来的那个电荷积分出来的那个电场，把这个微分就可以得到电场了嘛，Alright, so we also know that the equipotential surface, what is the equipotential surface look like if you have an infinitely long line charge? As you can see, it's only a function of r, so the equipotential surfaces should look like cylinders like this. So you have larger cylinders and smaller cylinders. The cylinders that is close to the z-axis has larger electric potential. Okay. So by taking the gradient of electrical potential in the cylindrical coordinate system, you should be able to find the electrical field intensity of this line. Okay. So the very last thing we like to show here, I might have a few minutes left, but let me finish this. So the last topic we have here is the magnetic vector potential built up by a static current. So intuitively, this should be similar to what we have with a point electrical charge. Point electrical charge produce electrical field. Small line current produce magnetic field. And in terms of what? In terms of magnetic vector potential. So equation 5.41 is what? Biot-Savart law or something? Oh, using the Biot-Savart. As you can see, it's very close to Coulomb's law. The magnetic flux density is proportional to IdL, inversely proportional to R to the square, related to the EM property of the environment. So you have mu over here, while in the Coulomb's law, the epsilon is in the denominator. And it's you have the 4 pi in the denominator as well. And the only difference is the magnetic flux density direction is always perpendicular to the current direction. This is the most significant difference. The E field is radially symmetric with respect to the point charge, while the magnetic flux density, the direction of magnetic flux density B is always perpendicular to the current I, direction of current I. All right, so okay, so the first thing is we try to identify B as this, as the gradient of 1 over R. 我觉得我今天讲不完了 ，OK 哈。So you should try this. If you perform the gradient of 1 over R in the spherical coordinate system, you should be able to end up with 1 over R to the square. That shouldn't be difficult to show. And so here is the okay. So here is the tool, the gradient for a scalar in the spherical coordinate system. So it's relatively simple. Just perform the differentiation with respect to R over here. So you end up with R to the square, 1 over R to the square. However, you need to apply this vector identity, which looks a little bit scary. So you should do this at home. Be sure you do this at home, okay? So you identify what? So here is the vector identity for any vector. When it crosses the gradient of a scalar, it can be expressed as the scalar times the curl of A minus the curl of the product of the vector N and scalar phi. All right. 我家己拢淡薄仔回去啊，好吧，下礼拜再讲好了。OK， give up。